All right, so we're going to continue our study with proofs. Last time we did algebraic proofs. So we did reasons for the box method, reasons for solving equations. Those are still going to be important today, but we're going to put all of this together back with some of the geometry that we know to do proofs for geometrical questions. So here's some things that we have. The way that this is going to work is the reason or the name that you would be writing down later is going to be all the way over here in the reason category. So this is the names I'm referring to, all the way in the reasons category. But if you notice, it's telling you vocabulary or concepts we've already gone over in other sets of notes. It's just putting it all together. The segment addition postulate is basically just saying that if we have two separate segments, AB plus BC, they would add together to make the largest segment. Yes? Does that make sense to us? If ever in a proof you're trying to tell me that the two small segments become the big segments, the reason is called the segment addition postulate. That's going to be the words we use. Now I'm going to remove my highlight on the reasons just because I'm going to need some of those colors to explain the reasons, but that's what I'm talking about, the reasons. If B is between A and C and points A, B, and C are collinear, then AB plus BC equal to AC. That's the segment addition postulate. The definition of midpoint. We know that midpoint is in the middle. Yes? The thing that we learn about that for midpoint is that if you have a midpoint in between A and C, then this length AB is equal to this length C. And that's again because of the word midpoint. It means that they are congruent. Congruent. In the same way, and almost with the same exact conclusion, instead of seeing the word midpoint, we're going to see the words segment bisector. If you see the word segment bisector, then again, you're talking about the thing in the middle of a segment. Well, if it's in the middle of a segment, then it creates two congruent segments, AB and BC. Okay, so none of this should be new. This is all review. Thank you. All review of things that we've done before. We're just putting it all onto one document. For the definition of congruent segments, that's the word you're looking for, congruent. Congruent means that they have the same measure. So if we know that they're the same measure, if we know that they're congruent, then we know that the measure of A and C are the same, or AB and CD. Seems like that all says the same stuff. Midpoint creates two congruent segments. Segment bisector creates two congruent segments. Thus, congruent segments mean that they have the same measure. Let's add that in there for ourselves, but I don't know if that's necessarily clear based on the notation. We're going to add in here same measure or length. That's what this is telling us. The other ones are telling us that they're congruent. This one's telling us that since they're congruent, they have the same measure or length. Those are all the postulates we know, or the definitions we have from segments. Once we talked about segments, we started talking about angles. So now we have a bunch of postulates and properties of angles that we're going to go over. So if we look at these angle relationships, the first one is called the angle addition postulate. Now I'm going to highlight very similar to what I did up on the segment ones. So let's say that we have a segment, or I guess it's a ray M, between the angle ARC. Well, what that tells us, let me zoom in here, is that if it's between it, then you have two other angles, ARM and MRC, that we can add together to make the big angle. That's called the angle addition postulate. ARM plus CRM equal to ARC, the bigger angle here. That's a whole lot of. Let me make that clearer. Let me make my drawing a little clearer because that was not very clear. So you've got your big angle ARC, you've got your small angles ARM and MRC that make up that big angle, and we know that because this little segment here in the middle is between it. That's the given. If you have a point in between the angle, then the two angles created by connecting those lines together add up to the big one, just like the segment addition postulate. Now we see another word that we saw a second ago. It said segment bisector a second ago, but now we have angle bisector. Bisector is a hint that it acts like a midpoint. So if the ray RM is exactly in the middle Okay, exactly in the middle. It has created two congruent angles. Your two congruent angles are ARM and MRC. We know this because of the word bisects, that it creates two congruent angles. Again, this is not new. This is stuff from a bunch of different notes put together into one formula chart here. Applying the word congruent to angles, we know that if two angles are congruent, if this angle is congruent to this angle, then their measures are the same. The measure of angle ABC is equal to the measure of DEF. That's what congruent tells us. Our hypothesis is that they're congruent. Our conclusion is that they have the same measure. Same exact rule for congruent for segment and angles. We haven't really used this word yet this year, but you've used it before. Perpendicular. Does that sound familiar to you? Yeah, cross streets where you meet at like a red light, for the most part, are perpendicular. If we know that two segments are perpendicular, let's say we know that AC and DB are perpendicular. Here's AC, here's DB. If we know they're perpendicular, then what we can conclude is angle DBC is a right angle. Angle DBC is a right angle. Does that sound like something we've heard of before? Perpendicular angles create right angles? Cool, cool, cool. We can draw that conclusion knowing it's perpendicular. Then we have the definition of a right angle. Knowing that an angle is a right angle means that it is equal to 90 degrees as a measurement. Straight angles would be equal to 180. Complementary angles, though, they should add up to what? 90, to that right angle. That's what we know. If we know their complements, then we know they add to 90 degrees. If we know their supplements, what do we know they have to add up to? 180. Let's just highlight those numbers right there. So if we're told that they're supplements, our conclusion is that they can equal to 180 degrees. Okay. On the back, those are all our geometrical properties. Then we get into the properties we kind of talked about last class, all of your properties of equality. So we're going to just go through these a little quickly. You have your addition property, which means you can add stuff on both sides without breaking the equal sign. So here's my plus on both sides. Therefore, if we have xy minus 10 equal to 32, then xy equal to 42. We would add 10 on both sides. We have our subtraction property, where we can subtract stuff on both sides and not break an equation. We have our multiplication property, where we can multiply something on both sides of an equal sign and not break the equation. And last but not least, we can divide by something on both sides and not break the equation. We did really well on this last time, so I'm not spending a ton of time here going over those four, but those are my inverse operations. That's how we've been solving equations for basically our whole life. Then we had our distributive property. The distributive property is like a multiplication to both terms inside the parentheses. Again, we recognized this pretty well last class, so I'm not spending forever on it. But then we have our substitution property, and not a lot of us noticed this when we all asked me about this one, so let me slow down for a second. If A equal to B, then A may be replaced for B in any equation or expression. So let's look at the example they gave us. They told us that, I'm going to color code this one, angle M plus angle P is equal to 90 degrees, and we know that angle M is 45 degrees. Therefore, I can replace or substitute angle M with what number in my conclusion? Let me maybe make this a different color. If angle M is 45 degrees, did anything change about my color coding from here to here? But what changed? There's no longer angle M here. What is there now? 45 degrees. And I substituted that in. So if something disappears and is replaced by something else, we have used the substitution property. That's the one that I don't think many of us noticed last class. And then we have our other properties of equality. Y'all were really good at recognizing these. XY equal to, or congruent to XY means that XY is congruent to XY. It's called the reflexive property. 4 is equal to 4. Duh. It's called the reflexive property. Then you have your symmetric property, which basically allows you to do what with your hypothesis and conclusion? Do what? Switch the sides of the equal sign. Change nothing, just flip-flop them left to right and left to right. That is the symmetric property. It doesn't break your equations. The last one is called the transitive. Again, y'all did really well recognizing this one. Let's say we have angle 1 equal to angle 2 and angle 2 equal to angle 3. That's my hypothesis. The conclusion is that angle 1 is equal to angle 3. This is the one that like cuts out the middleman. If these two things are both equal to angle 2, then they also have to be equal to each other. That's called the transitive property. Cutting out the middleman. Do most of these properties and things sound familiar to us? Yeah. Great. What you're going to do today on the other set of notes is use these 2 pages as a reference sheet to figure out the reasons for a proof. So if we look at this first example here, we want to give the reason for every single statement in this proof. Your statements are given to you. Your reasons are going to come from that reference sheet. So keep it available so you can look at it like a formula chart. Okay, we are going to try to use the, let me say some words that make sense. We're going to take the given, which was measure of angle 1 is equal to the measure of angle 3. First of all, let's make sure we understand what that means. That means we have this angle and this angle to be the same measure. We know this because it was told to us. We also know this from the picture of this lamp shining a light because of the little arcs. They tell me that they're congruent, or that they're the same measure. Okay, so let's put some reasons down here. What is the reason I'm allowed to make that first statement in a proof? This one word starts with a G. Start every proof with it. Given. Fabulous. So the first reason in any proof is the word given. Check, done. Then we look at what the next statement says. I'm going to color code them because I think it's really helpful to see the color coding in a proof. Here's my given. Angle 1, the measure of angle 1 is equal to the measure of angle 3. My goal of this proof is to show that the measure of angle DBA is equal to the measure of angle EBC. So we got some work to do to get there. All right, let's see what they've told us next. The next statement says that the measure of angle DBA is equal to 3, the measure of angle 3, and the measure of angle 2. Why are we allowed to say that this purple angle, DBA, is equal to this small piece and this small piece added together? What's the name of the reason from my reference sheet that allows me to take 2 angles and add them together to make the bigger angle? Absolutely. Angle addition postulate. So we're going to write that down. Angle addition postulate. I'm totally okay with you using short phrases for these as long as it's not just letters. I need to make sure you actually know what the words are. But postulate's kind of long, so POST period is fine. Addition ADD is fine. Okay, let's look at the next one. The next statement says the measure of angle DBA is equal to the measure of angle 1 and angle 2. Okay, what changed from statement 2 to statement 3? What's the only thing that changed? The numbers right here, yeah, the green and the blue. It was green a second ago, and now it says measure of angle 1 instead of measure of angle 3. Why am I allowed to switch that, to take that out and replace it with that? Because they're the same. And so what's the property we can use to take something out and put something else in its place if they're equal? Absolutely, it's a substitution. property? Substitution property means that I can take something out and put something else in if they are exactly equal to each other. Do we see that? Again, that was the one last time that most people asked me questions about. Okay, then we have the following statement. It says, measure of angle, that's not a highlighter, measure of angle 1 plus the measure of angle 2 is equal to the measure of angle EBC. Take a moment to look at our picture. We're saying this blue angle 1 and this angle 2 is equal to this red angle, EBC. Again, what's the name of the thing that allows me to take two small angles and add them together to make a bigger one? Angle addition postulate. Okay. We're obviously one step away from our conclusion here, but we need to make sure we know why. My conclusion, which is what I wanted, is that angle DBA is equal to angle EBC. Why? This one's kind of tough to see, just especially in the way that it's written. Let's look at what we know about measure of angle DBA. So this one, the purple, is equal, based on my color coding, to blue and red. What else is blue and red equal to? Wow, I said red. That's black. I know my colors. Purple, yeah. Purple is equal to, wow. Say your colors correctly, Miss Quigley. Purple is equal to blue and black. Blue and black is equal to what? Red. So these two colors are equal to both purple and red. What does that mean about purple and red? They're equal to each other, yeah. What's the property called where you can cut out the middleman? If two things are equal to a certain something, then those two things are also equal. No, but that's a good idea because they are going to be congruent. It's on the back of the reference sheet. Like the last one? Okay. Transitive. Transitive is the one where we're going to cut out a middleman. If I were to color this a little bit, maybe easier, don't add this color to yours because it's going to get really confusing. But if I just switch the color of this to orange, do you see that purple is equal to orange and orange is equal to red? Therefore, purple is equal to red. We can cut this part out since they're both equal to it. When you can cut out the middleman like that and make these two things equal, that's called the transitive property. Okay? Really a little bit confused. That one's hard to see, especially in a proof, because the stuff is all sorts of far away. But do you see in this proof how we took the statements they gave us and the picture and used the reasons from the proof's reference sheet to explain why I was able to do each step? That is what a proof is. You're basically arguing about math. Let's do another one together, okay? This one, we're going to be given that angle AEB is a complement of angle BEC, and we're going to try to prove that measure of angle AED is equal to 90 degrees. Okay, let's make sure we know what we're talking about here. We have angle AEB. That's going to be AEB. And it is a complement of BEC. BEC. Again, like I said, I find it easier to have these all color-coded. We want to prove eventually that AED is 90 degrees. Obviously, from the picture, it looks like it, but there is not the little corner box there, so we can't just say, it's a right angle, it's 90 degrees because of the little corner box. We're going to have to do a little bit more convincing. This proof gives you some of the statements and some of the reasons. You got to fill in what's missing. So the first step in this proof says that AEB is a complement of BEC, and the reason was given. Makes sense, that was what you should always start with. Then it says the reason is that it is the definition of complementary angles. Look at your reference sheet for the definition of complementary angles and tell me the conclusion we can draw there. Where it says definition of complementary angles, what's the conclusion we can draw from definition of complementary angles? It's you're looking at the then column of your reference sheet. If I'm looking at it, it says definition of complementary angles. The then statement says the two angles should add up to what degree? 90. That's what we need to write down here. So we're going to say that the measure of angle AEB plus the measure of angle BEC should be equal to 90 degrees. We know this because of the definition of complementary angles. It's what we were given, so we make a conclusion based on it. Okay, our next statement says that angle AEC is equal to measure of angle AEB and the measure of angle BEC. So that's the purple equal to the red plus the blue. Why am I allowed to say that those two small angles will add up to the big angle? What's the reason on our reference sheet where we can take two small things, add them to the bigger one? Angle addition postulate. Our next statement says that the measure of angle AEC, that's the purple angle, is equal to 90 degrees. How am I allowed to make that conclusion? Cool. Yes, I agree, but we haven't technically said it's a right angle yet. I know we know that it is because of the way that it is, but we haven't stated that in our proof. Here's what we know. Look at my color coding. Purple equal to black. How could I get the purple to be equal to the black? What are both purple and black also equal to? Blue and red. If they're both equal to the same thing, can't we make them equal to each other? It's the one that starts with the T. What's that property called? Transitive. That's the transitive property. If two things are equal to something else, they can be equal to each other. That's the transitive property. The next row gives us the statement and the reason. It says measure of angle AED. So that's AED is my green. Oop, that's not a highlighter. And the measure of angle AEC is equal to 180 due to the definition of supplementary angles. Cool, they gave us all of that. Therefore, I want to use the substitution property to make a next statement. Substitution means we're going to take something out and put something in its place. What could we put out or take out and put in the place of 90 degrees? Wow, I just said the answer. What could I replace measure of angle AEC with? Well, what is the purple equal to? 90 degrees, right? So we can substitute that in. If that's what it's telling me I need to do, we would take the measure of angle AED and substitute it. That purple gets substituted with the black 90 degrees. That's the substitution property of equality. Let me answer the phone. We just need to make our last reason here now. We have on our seventh statement that the measure of angle AED is equal to 90 degrees. How could I get 180 degrees to become 90 degrees? Subtraction. And subtraction, I would just subtract 90 over here and over here, yeah? That means that we are using at the last step the subtraction property. You can subtract things on both sides and they don't break the equation. Our last proof is a segment. This time we were given, if we color code, that AB is equal to BC, and we want to prove that AC is equal to 2 BCs. Okay, they've given us all the statements on this one. We just need to do the reasons. So the very first thing is AB equal to BC. What's the reason we're allowed to say that? Thank you. Given always starts off my proofs. Check, done. The second conclusion or statement that I make is that AC is equal to AB plus BC. How come I know that that big segment is made up of adding the two small segments? What's that property called? Yes, but we're going to call it segment addition because we're dealing with segments. But it is the addition postulate, so segment addition postulate. Okay. The next statement says that AC is equal to BC plus BC. What happened there from statement 2 to statement 3? It switched to what? Yeah, AB became BC. Why are we allowed to take AB out and put BC in its spot? They're congruent to each other. They're the same. So we've substituted AB and BC. If they're equal to each other, then we can use them interchangeably. We can substitute them. Take one out, put the other in its place. Then the last statement here, which is what we want to prove, is that AC is equal to 2 BCs. Now this is not actually on your reference sheet, but when you have two of the exact same things and you're adding them together, I always call it this 3 letters. What is it called when you take two things and add them together, make it simple? 3 words, but 3 letters. It's not on your reference sheet. It was one of our reasons for the box method last time. It starts with the word combine. Like terms. We can just simplify that by combining like terms, and thus we have made our final conclusion. Now last time each of our proofs ended with the cute little box. If you still like that, you could put the cute little box at the end of each of these proofs to say that we're done. I always like it because it's kind of fun. I love fun and funky symbols. Proofs are tough because it does require you to have a reason for every single step in a problem. So how we're going to practice this today is with a gallery walk that's out in the hallway. Now this gallery walk in the hallway is on white pieces of paper, which means they're kind of hard to see, but I've gone ahead and I've highlighted them for you just like I did on our notes so that you can try to answer each of the questions.